This is the third and last video of the series. I'm going to talk about scattering maps and the classification of scattering maps. It's part of the series of lecture about results, new results about the Einstein constraint equations. And this part is about the gravitational singularities and how you can cross singularities and still be able to define a solution to the Einstein equations. There will be two parts, two sections. And this is a joint work with Bruno LeFloch and Gabriele Veneziano. We are interested in the problem of bouncing cosmology when you have a solution of the Einstein equations describing a certain space-time. And within this space-time, there is a phenomena of contraction followed by an expansion. And the key question is how you connect the contracting domain of the spacetime to the expanding domain of the spacetime. There have been classes of physically meaningful junction conditions proposed in the literature, but no classification and no idea how you should actually select them. Of course, there are junction conditions in the literature several decades ago by Israel, but the junction conditions that he defined are for regularity hypersurfaces. In my situation, when the hypersurface is approached, the metric is singular, the extrinsic curvature is singular, so these relations would not apply. The second remark I need to make first is that the asymptotic near gravitational singularity was studied decades ago by Belinsky, Kalashnikov, and Lifshitz, and they realized that there are two distinct regimes, one being highly oscillatory and one being more monotonous or quiescent. And this is a regime I will cover in my lecture. Mathematically, the existence of solutions to the Einstein equations in terms of dynamics, going toward the singularity or going away from the singularity, has been studied in the past 10 or 15 years by several people. But again, my issue is not so much to approach the singularity or to leave the singularity, but the question I'm posing here concern the junction between one contracting region and one expanding region. We are going to do that in the regime of coupling of a scalar field, or it could be also stiff fluid or compressible fluid techniques would also apply. It could be vacuum, but it would then have to be in higher dimension. I'm going to introduce some basic notions. I mean, which are maybe not so basic because you have to think a little bit about what sort of asymptotic is valid near the vicinity, in the vicinity of the gravitational singularity in order to figure out the right variables. But it will turn out that we can define quantities denoted by G, K, phi 0, phi minus on one side or the other side of the singularity. And then the main question is how you connect data from one side to the other side. And we are going to do that by introducing what we call a singularity scattering map. Having done that, and this will be the main issue for this lecture, comes the question of constructing spacetimes that follow follow this junction, and we call such spacetimes S-cyclic spacetimes. And we have also a construction of spacetimes of that sort, but this will not be my main concern. To have a global construction, this is possible, at least under certain symmetry conditions, and I will, you can refer to the papers for about that. So the main question for this lecture is a classification. What we do here is that we work with general spacetimes. We rely on the constraints, but in fact, an asymptotic version of the constraints. All the earlier works were concerned with symmetric spacetimes, spatial junctions, and that's not our goal. Our goal is to have a full classification. And we will see that this classification covers what we call universal laws and model-dependent laws. So there are two aspects in the junctions of aspect of universal type or model-dependent type. And that's probably the main contribution of this work, to realize that there is a classification, very few degrees of freedom, and therefore you figure out degrees of freedom that are model dependent, and the rest of the construction, which is something universal. The way to set up the problem is to introduce the ADM formulation of the Einstein equations, defined by a Gaussian foliation. So tau will be the Gaussian time, and the metric, the four-dimensional metric, is written as minus d tau squared plus g of tau. G is a Riemannian metric, so you will soon realize that the problem I will face is actually a curvature problem in Riemannian geometry. And then I'm writing the evolution equations that come from the Einstein field equations. So d tau of the metric is equal to the extrinsic curvature. This is, in fact, the definition of the extrinsic curvature in this foliation. And then the evolution of the extrinsic curvature is given by the formula here. And there is a misprint that intrinsic should be extrinsic. The constraints are, of course, essential in all the construction, Hamiltonian and momentum. I'm going to write them again in some asymptotic form soon. We have also coupling with a scalar field, which may be governed, its evolution is governed by a wave equation. And I remind you that the Einstein flow, defined in this way, has been studied by a number of people, including Anderson, Lott, Moncrief, Reyes, and other people. So I built on their contribution. The flow exists, but the flow is defined possibly up to the singularity or from the singularity. And I'm going to define certain rescaling of the flow solution as we approach the hypersurface. They are called G plus K plus phi 0 plus phi 1 plus on one side, and there is a minus subscript or upper script on the other side. And we are interested in connecting the two. But before we can even pose the question, I need to tell you how I define this rescaling of the metric and the extrinsic curvature, etc. So let's do that. So to introduce the notion, I'm just reminding you that there are special solutions to that, called the Castner profiles. And I'm writing them where K star, you can see the diagonal, it's 1 over tau minus 1 over tau times the diagonal. The matter field is a log of tau plus a certain function. The coefficient in front of log of tau depends on x. The lower order coefficient is also a function of x. And similarly, the metric has a power form, and the exponent are denoted by P1, P2, P3, they depend on x. Now, this can be actually an exact solution, but only when the Pj are constants. This will be exactly the Castner spacetime, not just an approximate solution. But this is the way I'm going to see it when there is a dependency in x. I'm going to view that as an expansion, giving me an asymptotic profile for the metric and the extrinsic curvature. And it has some additional constraints I'm going to write, but that's not important immediately. So what can be done with this ansatz? This ansatz will be transformed into an actual solution by using Fuchsian techniques. So you can think of imposing certain singularity data on the singularity. They generate an ansatz for your solution to the Einstein equations locally. And then by a sort of iterative technique, you produce an actual solution. And behind this construction, there is this idea of having an asymptotic ODE system. So what is going to be constrained will be only the dependency in time. So this is done in the context of the so-called velocity-dominated ansatz. All the spatial dependency can be removed, and by applying Fuchsian type argument from the singularity toward the future or toward the past, you construct an exact solution to the Einstein equations, which is in agreement with a certain ansatz that you prescribe on the singularity. Our standpoint is to study the asymptotic data, to study the constraints that they have to satisfy, and then to ask how they can be connected. There should be a certain junction to connect them. So this is the issue for this lecture. We are going to call a singularity initial data set, and we can specify past set if necessary, on a 3-manifold as being 2 tensor fields denoted by G minus and K minus, 2 scalar fields, phi 0 minus phi 1 minus, and these fields are assumed to be as follows. G minus is a Riemannian metric, K minus is a 1-1 tensor with unit trace, symmetric. So CMC that is behind our construction implies precisely that the trace is 1. This is one of our constraints. And the Hamiltonian constraint takes the following form. So 1 minus the norm of K square is equal to phi 0 minus square with an 8 pi factor. And the momentum constraints is taking the following form. The divergence of the tensor K minus is given by basically the gradient of the matter field of the phi 1. Now, all the set of G minus, K minus, phi 0 minus, phi 1 minus satisfying all these conditions would be called the space of singularity data, denoted by I of H. And this is with this set that I'm going to work. If you give me an element of this set, I can generate an asymptotic profile by certain exact formulas that mimic what I gave you in defining the Castner profiles. So G star of tau is a certain power of tau, but this involves the tensor 2k minus times the metric. K star is simply a rescaling of k minus, and phi star has a log tau structures that I mentioned before. We are interested in the regime, in the monotone regime or quiescent regime, where k minus is positive. A scattering map, or more precisely, a past to future singularity scattering map, is a map that takes an element in I of H and maps it to an element of the same set. It has to be diffeomorphism covariant. So in some sense, you don't want your construction to depend on coordinates. And so the only condition that I'm really imposing here is a locality property, which you could argue geometrically or physically that maybe some other condition would be better, but that's not our point of view here. We localize, we assume that the junction will be local in the sense that I'm writing here. The restriction on any open set depends only on the restriction of the data on this open set. So it's local in that sense. And soon I will tell you that I'm actually interested in a pointwise or ultra-local definition. But let's wait a minute for that. Based on such a map, we can define the notion of S-cyclic spacetime. It's a manifold, four-dimensional manifold, with a Lorentzian metric and a scalar field. And you, in this definition, you assume that you can decompose the manifold into a regularity domain where, so it's a regularity domain defined through a singularity locus called L script. So outside this locus, the Einstein equations are satisfied for the metric and the matter field. And now I need to tell you what happens on or in the vicinity of the singularity set. And following what I already introduced, I'm assuming that there is a local Gaussian foliation for in the neighborhood of each point with the same structure I told you before. And based on such a foliation, I'm now imposing the junction conditions at each point of the singularity set. So it's going to relate the future to the past singularity data, which I denote by G plus minus, etc., like before, and which I define by taking suitable limits of my metric. So in this definition, I'm assuming that these limits exist, but it's not, in some sense, it's not a restriction, because this is what we have seen to be true when we constructed in a previous slide actual solutions to the Einstein equations by Fuchsian techniques. So this limit for a solution constructed in this setup, these limits exist. And I take this value and I'm imposing in this definition that the limits on one side and the other side are related by the prescribed S map, the map S. So this is our definition. At this moment, I'm only talking about local construction. This will be the next slide in the classification. But let me repeat that we can do a global construction in a plane, or more generally a T2 symmetric situation, that a construction that uses exactly this notion of S-cyclic spacetime. The regime of quiescent preserving bouncing suggests to assume on the map itself that K plus is positive whenever K minus is positive. And now comes a local theory. You give me a three manifold and a quiescent preserving scattering map in the sense of the previous line. You also give me certain data on the singularity on one side of the singularity, and then I can define in the past, in the future, a solution that is S-cyclic in the sense that I explained a minute ago. Now this space-time, so it's really a local construction. It's an easy construction, but it somehow provides some support to the theory. So if, in addition, if the hypersurface is compact, we can prove that the volume of the slices is shrinking to zero when we approach the singularity. The singularity is crushing in the sense that the mean curvature is blowing up. It's normalized to be asymptotic to -1/tau. And the curvature is also blowing up in a way that we can also compute the asymptotics of this four-dimensional scalar curvature over tau squared, the limit of that. So the technique of proof is what I just said, the Fuchsian technique, gluing technique. So we glue construction to the future and a construction to the past. We glue them according to our map. Okay, that's not difficult, but again, it gives you the notions that we believe are the right notions to talk about this problem. And now let me move forward and now discuss the classification of these maps. Again, this is a joint work with Bruno LeFloch and Gabriele Veneziano. So as I mentioned before, we impose what I put in this definition here. We impose that the map is ultra-local, or you could say also pointwise. So what this means is that the locality properties that I defined before tells you that the expressions of the map S of its argument at the given x could depend on the value at x, but also possibly derivatives. Okay, so we are not including that, and we believe that this is physically or geometrically quite reasonable. So we work with so-called ultra-local or pointwise maps. Now, this being said, you can define still sub-classification, and we have done that by imposing some further conditions, but these conditions are not really restrictions. They are introduced to give you some subclasses in our general classification. So for instance, you can ask that the two metrics at certain times, 2 minus 2 plus, before, after the singularity, differ by conformal factor. Or you can impose something somewhat stronger, which we call rigidly conformal, when the asymptotic metric G plus is conformal to the asymptotic metric G minus. And then you can continue. We have also notion of momentum preserving maps, momentum reversing maps, etc. And such notions are especially idempotent or invertible. They come of special interest if you want to treat time-like hypersurfaces, which I'm not discussing today, but our framework also covers time-like hypersurfaces. But for today, I'm mainly focusing on space-like hypersurfaces in this presentation. So what are our strategies here? So we rely on the constraints. So you remember that we have G minus K minus phi 0 minus phi 1 minus as our data. These data satisfy certain constraints. The first two constraints are algebraic in nature, but the third one is a differential constraint. So we start with that, and we analyze general solutions of these constraints, not imposing any symmetry restriction. No symmetry. We construct suitable classes of singularity data that help us to, in some sense, to probe the properties of the scattering maps. So we assume that there is a certain scattering maps, but we want to classify all possible maps. So we don't know much about it, except that it is ultra-local. And by simply probing the, these maps using the constraints, we are able to identify the degrees of freedom for the junction. And what is remarkable is we realize that there are very few free parameters, degrees of freedom when you want to pass from a contraction to an expansion. You cannot do anything. There are constraints. The constraints are precisely the one I wrote in red above, but they do imply strong restrictions on the junction. So this is our contribution, and we continue and we get a complete classification by following this idea. The way we present our result is first to treat a simpler class of rigidly conformal maps, because the result is simply easier to grasp and to understand. But in fact, there is a general classification behind. So let me now summarize, and we arrive to the main result for the lecture today. So the class of rigidly conformal maps consists of only two elements with a certain parameter, but basically two classes, I should say. So two classes of ultra-local space-like rigidly conformal singularity scattering maps for self-gravitating scalar fields. So the first class is defined. So what I need to tell you what are the data after the crossing the singularity. So I give you G plus, K plus, phi 0 plus, phi 1 plus in terms of the incoming data. And the formula are written in red on the screen. And you see that the metric after the singularity is a conformal multiple of the metric before, where the multiple depends on the matter content, phi 0 minus, phi 0, phi 1 minus. This defines the matter content of the spacetime, and it depends on the determinant of K minus. Now, interestingly, K plus is simply is trivial, right? It's just delta, the round metric, 1/3 of it. And so it has forgotten, in some sense, all the information from before, from the past. And the same phenomena happens with the matter field. So you basically forget about some geometric and matter content information, and you rescale your metric by a certain function of what you had in the past, but only what I wrote here, the matter, and only the determinant of K minus is relevant. And the constant phi is really not, it doesn't carry very much meaning of physics. Okay, the second class is something we call non-isotropic rigidly conformal bounds. It's more involved. So you can look at the formula and see that now you again prescribe the metric and K plus, phi 0 plus, phi 1 plus by a certain formula. So these formula maybe are not as simple as before, but still they are parameterized by very few information, I would say. So on the singularity, you only need to know a constant C, positive, and a function of a real variable. So if you give me that, from this small f, I can construct a big F by a simple integration. And from the small f, I also construct the conformal factor mu. You plug this mu and this capital F in the formula before, and you know exactly what is the geometry after the bounds, only from these two things. So if you think of it, there are really, in principle, a lot of degrees of freedom, but we reduce all the degrees of freedom to only the knowledge of a constant, small c, and a single function of a real variable. So now I'm not going to give the general classification here, but the result is exactly of the same spirit. Only two classes of ultra-local space-like singularity scattering maps for self-gravitating scalar fields, isotropic bounds, similar to the one before, non-isotropic bounds, also very similar. Now, lambda comes to be a two-tensor, and phi is something we call canonical transformation of the matter, and we also have a constant c. So although I'm not going to give you the formula, but we have the formula, everything is completely explicit, depending only on these parameters. What I can do, I can somehow restate this result with a different point of view. And this will be one of the last slides of this lecture. So we can actually present our result as in the following form. We discover that at a junction, there are three universal laws of quiescent bands in cosmology. So this is what we propose, we discover. There is a first law, which is a scaling of the Castner exponents, given by the expression in red. So there exists a constant, gamma, such that you connect K plus and K minus on one side as written on the screen. The zero means that you only look at the traceless part of the extrinsic curvature. Then there is a second law, which we call a canonical transformation of the matter. There is a certain map that takes matter variable before to matter variable after the bounce. But this map is very much restricted. It preserves the volume form in the phase space for the matter components. And it depends only on the scalar invariant, the determinant of K0 minus. And the third law has to do with the metric, and we call it directional metric scaling. And you see that G plus and G minus are related in the way I wrote. There is a nonlinear scaling in each proper direction of K, with, again, two possibilities: isotropic scattering or non-isotropic scattering. With, in the first case, there are no restrictions on the values of sigma 0, sigma 1, sigma 2. So then the formula is really very easy to read and to understand. And when gamma is non-zero, we have explicit formula in terms of this nonlinear map, capital phi and the constant gamma. So let me give some concluding remarks. So we believe that our standpoint is a way to attack now specific theories and we can now realize that we know what's the missing information somehow. This classification tells you that there are very few degrees of freedom at the singularity. So you should somehow look for these degrees of freedom, these functions, from specific models. And the specific models that you find in the physics literature are the so-called pre-Big Bang scenarios proposed by Gabriele Veneziano and colleagues, the modified gravity matter models, the loop quantum cosmology models. So there are a whole zoo of models which we are now looking at. And this classification and the fact that we have universal laws and model-dependent laws should provide a good guide to uncover the relevant structures behind this. So what we call universal, again, means that we have junction conditions that are independent of their origin from different microscopic corrections. So you can take any of the models on the top of the screen, and they will actually give you the same universal junctions. These junctions are satisfied for each of these models. So let me conclude by saying that my interest personally in singularities for the Einstein equations go back to joint work as I did with Alan Randall about 10 years ago, and John Stewart in Cambridge. And more recently, I just did this work with Gabriele Veneziano, and you can read the papers on arXiv, and a summary, the Physics Review D papers is a short paper that can give you the first introduction to the subject. And we also have with Bruno LeFloch a couple of papers that you may also be interested in. So thank you very much. Thank you for, it was a pleasure to do these 3 videos, and thank you again.